This week we're going to talk about IDC and SLC circuits. These are basically all the input circuits that we use. So I have a few definitions to go over before we dig into how they work and what makes them different and that kind of thing. So the first things I want to talk about is just the absolute basic, what is an alarm, trouble, and supervisory condition? I think the alarm is the one everyone in the fire alarm industry and out of the fire alarm industry is familiar with. This is the one where the lights and tones are going and the fire truck's being called and there's something gone wrong in the building and it's got the evacuation signal going. Trouble and supervisory are the ones that I think a lot of people either don't know the difference of or they don't know what they are at all. They're incredibly similar. In fact, the main difference is whether or not it's a trouble that's inside the fire alarm system itself or just something that the fire alarm system is watching for troubles. So for instance, if one of your power supplies has a battery going down or an open circuit happens or a ground fault, those are all going to be types of troubles. Supervisories are going to be things like, oh, your sprinkler fire pump lost power. Well, that's still a trouble that's in the building. It's not an alarm. It's not something you evacuate the building over, but it's not about the fire alarm system specifically. It's about the sprinkler system. So it's a system that is being supervised by the fire alarm system to monitor for its troubles. That's the only difference between a trouble and a supervisory signal, is one is an internal trouble to our system and one is a trouble that is outside of our system that we are supervising, and that's the supervisory. Some common ones that we see on just about every job are duct detectors and sprinkler tampers. The next two definitions I have are IDC, which is initiating device circuit. If you ever hear about conventional panels, zone circuits, that's what these are. We're going to dig more into that in the next slide, so I'm not going to go too much there. And then SLCs, that is your signal line circuit. That's kind of what's replaced IDCs for a lot of the part, but we still use the IDCs for certain things. And again, we'll get into that more as we go. The next thing we need to all know what it is a T-tap. This is a way that we connect another device to a circuit without just looping it through. So in all of our Class B circuits we've been talking about so far, everything has gone from one device to the next in just a straight line. A T-tap is where we take that straight line and you put another device, say, if you're looking at it on a piece of paper, say you put it below it and then you drew your wires down to connect to that device, it would make the shape of the letter T. So that's where it gets its name T-tap from. This is really common with SLC circuits because we can add, a single smoke detector or something over in another room, and we can just throw one quick wire over to it. But we're going to talk about how with NAC circuits, Class B, end-of-line supervised type of circuits, and IDC circuits, we're not able to T-tap. And then the last definition word I have here is a loop. This is a pair of wires that form a complete circuit. So if you think about that diagram that we've been using for our Class B circuits, you've got a positive side and a negative side, and you can trace it all the way around and it just makes a big loop like an oval shape. That's the path the electricity is following, and so that's become kind of the common nomenclature for what a loop is. So as we talk about loops and T-taps, I hope that helps make sure everyone here understands what they mean. So now we'll dive into IDC circuits. These are the initiating device circuits. Just like our NAC circuits and our speaker circuits that we've been talking about, these have an end-of-line resistor and they're supervised that same way. So we cannot T-tap this kind of circuit. If we have to add a device to a circuit, we have to actually pull two wires over to it, one to send the signal to the device from and one for the signal to come out of to rejoin the initial circuit, interrupting the circuit's original path so that it has to flow through the new device the same way it flows through the others. We cannot T-tap any kind of these circuits that are the Class B supervised with that end-of-line resistor. And as far as troubleshooting these circuits go, it's going to be the same way we've been talking about with the NAC circuits. Everything from ground fault to opens and shorts and checking for end of line, all of it, we're going to test it the exact same way as far as, using the meter to check for continuity and all that. Now we'll get into the way that the circuit actually kind of works and what its function in the building is. So the way this works, that's different than a NAC circuit. If we get a short circuit on a NAC circuit, the circuit actually stops working. That's a bad thing that we don't want to happen. With these initiating device circuits, that short circuit is actually how an alarm is caused. So one of the ways that we still use these IDC circuits today is when we monitor our sprinkler devices. We'll use the common and normally open terminals, and then when that water is flowing, it pushes a switch that then closes those terminals, causing a short circuit, and that gives us the alarm of the water flow device. In older systems that had zones, you might make this whole hallway one zone and the other hallway on the other side of the building a separate zone. And then they've got their smoke detectors down the hallway. And when one of those smoke detectors goes into alarm, it has contacts inside there that close the connection from one side of the circuit to the other, causing that short. And your panel will tell you, hey, you have an alarm in the north hallway or an alarm in the south hallway. And that's why they were called zone systems, because they work by zones like that. They didn't report individual devices, they reported the whole circuit. So if you have a problem on that circuit or you have a problem with one of those devices, you're going to have to travel the whole length of that zone. You're going to have to walk down it, look and inspect and everything else to try to figure out where it is. The same as if there's a fire and it's reporting an alarm. You just know that the alarm's in that section of the building. You don't actually get the individual device reporting off of these IDC circuits. One of the benefits of them was it was an easy way for technology to supervise fire alarm when technology was much further behind what it is now. The computing powers of when these circuits came out, in order to do what our fire alarm panels do now, it would take like an entire floor of a building then. But now we can fit that in a little box. So we needed something much simpler to run, and that's where these IDC circuits came in. Also, they're quite a bit cheaper. So one area we still use them for conventional panels is apartment complexes where we're just doing some sprinkler supervision, and then we'll go around the apartment complex and just monitor all the different panels at each building. That's a very cost-effective way to get a system like that done that leaves each building standalone without having just incredibly high prices. Also, kitchen hoods work this way. All the sprinkler devices work this way. And we monitor all those with monitor modules. Anything we do with a monitor module, that secondary side of the module, is one of these IDC circuits. We can also run across in service applications where we run across an old conventional system. All those conventional systems are this, and they all work the same way, whether it's a monitor module or conventional smokes or conventional heats. Those conventional heats we still use a lot of times in parking garages for elevator recall. So those are a handful of ways that we use these even still today. And then what we've replaced it with is much more intelligent, much more efficient, but it's also much more expensive. And that's the SLC, the signal line circuit. This is a loop that constantly carries communication between the panel and each individual device. They're always talking back and forth. One of the things that's important to know with this, especially when you're talking to a fire marshal, and it's the sub-bullet under that first point there, the panel is what makes the alarm decision here. So in that IDC circuit, there's not really information communicated back and forth between your control panel and your device. It's just, is the device shorted, yes or no? So your device is kind of making your alarm decision in those situations. With SLC and these more intelligent devices, your devices are actually sending the specific readings, the specific percentages of air to smoke that's in the device or how hot it is to the panel. And the panel is actually what's determining, okay, is this an alarm condition or not? So there's been some times with fire marshals where that's come up, and they seem to think that something's wrong with the device because of it not making a decision, but the device actually doesn't make the decision, the panel does. Also, the devices in this case are individually supervised by digital communication. That's that talking back and forth constantly. We're going to get into polling types in the next slide, and I'll talk more about that there. But also because of that individual communication from each device to the panel, T-taps are allowed unless we're in Class A, because that's a whole different purpose. But most cases we're not in Class A. The Navasota ISD, we have the Brozig Auditorium coming up. That one, they're requiring us to put the SLC in Class A. Every other job we have on the books right now, we don't have to worry about it. On the drawings of that one, I laid out how to pull the SLC. So if you just pull it the way it's drawn, you shouldn't have a problem. Something I forgot to mention with the IDC circuits, because it's the whole circuit that initiates the alarm and the panel can't talk individually to the devices, you can't mix supervisory type devices and alarm type devices on those IDC circuits. So for instance, if you're monitoring a sprinkler system and you got one water flow and one tamper, you have to pull two separate zones over there, one to monitor the tamper since it's a supervisory signal, and one to monitor the alarm, which is the water flow. You're not able to just use the one circuit to pick up both devices because you've got two different types of signals. On these SLC, we can pull just the one SLC loop in there, and it grabs both monitor modules on that primary side, and it can mix the alarm and supervisory devices on the same circuit. So that's another big difference between SLC and IDC. Also with IDC, if one device on your circuit goes into alarm, the whole circuit kind of drops out and you don't get any more alarm signals from that circuit. It's only capable of seeing, like once it's shorted, it's shorted. You can't get multiple shorts. It doesn't say, oh, you've got 3 shorts on this circuit, so you've got 3 alarms. It just sees short, so it just says alarm. With SLC, you can get multiple alarms at the same time. And of course, we can also report the device specific descriptions and events. So you can have supervisories being reported at the same time alarms are being reported. And you can have different smoke detectors going off, and you can have different duct detectors going off, or multiple sprinkler alarms, or any combination of those. And monitoring is able to get the information and relay it to the fire department. So if there's, they can track kind of, okay, is the fire spreading or is it just staying in this one room? So that's what SLC is. And in the last slide, I talked about as far as troubleshooting goes for the IDC circuits, you do it the exact same way you would troubleshoot a NAC circuit. Signaling, the SLC is a little bit different. We're not supervising it with an end-of-line resistor because all the devices are talking. So if you're trying to figure out how to meter it before you wire it up to your panel, say it's you and a helper there, send your helper to the far side of the building, you stand at your home run, and you can still set your meter to that resistance setting and check the meter, and with your helper on the phone or on a walkie-talkie or something, tell them, hey, short these wires together and open them back up, and you should be able to see them shorting and opening them up on your meter there. If you can't see that, that means that you have an open circuit somewhere between those 2 points. Also, you shouldn't see a short circuit at all on SLC. That'll keep the whole circuit from functioning, and you'll check it for ground fault the same way as well. The same way as NAC circuits, that is. You know, one meter lead connected to a good ground reference, and then you check both wire conductors with the other meter lead. And if you see any continuity from earth ground to your wires, that means you have a ground fault. And if you don't, then you're good. So that's kind of the big difference between checking your SLC for open circuit versus checking one of those other Class B type of circuits that have the resistor at the end. Is instead of having a resistor at the end, you send your helper to the end and you open and short the wire that way, and you should be able to see what your helper's doing. And then so to get more specific, told you we were going to talk about the SLC polling protocols. on the left-hand side here, I have clip protocol, which is classic loop interface protocol. When SLC first came out, this was the only way it was done. And the addressable devices in the clip protocol, they communicate to the panel one at a time. And the larger the system is, the slower it reports because they go in order. So one reports, then two reports, then three reports. And so if you've got 100 devices, it's got to go all the way through the line. On the other side, I have velocity, light speed, and flash scan. Those are all the exact same thing, just depends on which brand system you're on for system sensor devices. Velocity is the term that Gamewell uses. Light speed is what Firelight uses. And I think Silent Night also uses light speed. Silent Night doesn't, they don't make it real clear. They kind of go between velocity and light speed because they're borrowing everybody else's documentation for a lot of stuff. And then flash scan is what Notifier calls it, but it's all the same thing. It's this is specific to the system sensor type of devices, which are most of the devices we put in. They're either system sensor or Hochiki. So whether it's IDP or the ASD PL3s or SK, they're all made by system sensor. So they use this protocol. And what it does is it talks to 10 devices at a time instead of one. So if you wire up 4 modules and say you address them 11, 12, 13, and 14 and stick them on a wall in front of you, like maybe you're in a high-rise fire riser room and you've got these 4 modules here. In clip mode, if you stand there and you watch those 4 that are sequentially addressed right in front of you, you can actually watch them flash in order every single time. It'll just just hit each single one. If you're on a system that has the velocity or the light speed, which the E3, the S3, those are both velocity systems. The 7100 was a clip-only system. You'll actually see all 4 of those modules flash the same time on the velocity. The recent update of Silent Night moving to the Black Series panels away from like the 5820 or the IFP 1000, those were all clip mode only panels. And now the Black Series is this velocity light speed. They haven't really named it for Silent Night, is why that's confusing. But it's the same protocol where it talks 10 at a time. And also, the real reason it's important to know this is I have 2. One of them Colin can attest to. We stayed out one night till like 1 or 2 in the morning at some stupid little high-rise where we were changing a panel out and couldn't figure out why we couldn't get half the devices in the building to communicate into the panel. And so we were out there really late just we were testing everything. We had the right voltage at the device. We'd move the device around, change addresses, but we knew the device was fine because it was talking to the old panel, but why isn't it talking to the new panel? Well, it turns out we needed to have clip mode enabled on it so that the panel would know to only talk to 1 at a time, because those devices we were having problems talking to were older devices. And it had a lot of newer devices in the building, and all the newer ones were talking just fine in the light speed protocol, because that was a Firelight system we were working on that night. But it had some of the older devices, and there's some older modules, some older mushroom head type smoke detectors that would only talk on clip, and those were the devices we couldn't figure out why they wouldn't talk. And I think what happened was we wound up getting on the phone with Mike, and Mike made us feel stupid because he asked if we had clip mode enabled. And sure enough, we did. And then as soon as we clicked it and downloaded that program in with clip mode enabled, everything came up and talked, and we could have gone home hours before and been in bed a long time before, and that would have been nice. So that's one reason why it's important to know that there is clip mode out there. You need to be aware of it. The other reason it's important is with these new bright white devices that we got, the bright white smoke detectors and heat detectors are not clip mode compatible. They cannot be put on the same SLC loops as those older devices. But if you get the Ivory variation of it, the exact same device, but now with an Ivory housing on it, they made the internals of that be compatible with clip and velocity so that you can talk to both the newer systems and the older systems with the Ivory devices, but not the white devices. So if you're working on one of those older systems I mentioned, like the IFP 1000, the 5820, the Gamewell 7100, all of those panels are clip mode only. So if you put a bright white device on that, your panel's not going to talk to that device. But if you put an Ivory device on it, it'll talk just fine. And when they were first coming out with it, my first thought was, well, we just need to put all Ivory devices everywhere, because then that's what we'll have in stock, that's what we'll have available. But there's a pretty significant price difference between them. And so we realized it was beneficial in our favor to go ahead and put the white devices in all the new systems, and then we'll just have some Ivory devices we keep on hand for service applications. So if you are going on a service call, if you are working in an older building, make sure you know what type of panel you have and what kind of devices it communicates to. With that, I think that's kind of all I had to say about SLC and IDC and polling protocols and all that kind of stuff. If anyone has any questions or something they want to bring up, feel free to. Do you have anything you want to add, Mike?
Yeah. Keith went over very quickly some stuff on the older circuits. While we were sitting here talking, what we're going to do is we're going to have a future class on older systems, just so you guys know and understand, if you walk into it, what some of these older systems did and what they look like and how they operated. One of the things Keith kind of touched on was the fact that those initiating device circuits shorted. That's true, and it's not true. Just so you know, in case somebody's scratching their head there, if you had an old zone system with smoke detectors on it that was called a 2-wire smoke detector, which basically meant the panel provided the power to that smoke detector. And the way that actually worked was your smoke detector would go into alarm. It wouldn't short, it would put a draw on that circuit, and that circuit would see that the resistance on that circuit went up just a touch, and that would put the circuit in alarm, the smoke detector in alarm, and leave enough voltage and current available on the circuit for that smoke detector to light its individual LED. So anyway, and then there was also smoke detectors that would short. They were called 4-wire smokes. You ran a separate power to them. A lot of this got actually fairly complicated in the wiring back in the day. So we're not going to go into all of that right now. Just kind of know in the back of your head that some of that stuff's there. As far as the SLC circuits, bear in mind that what we're talking about here are the products we use, the Silent Night and the Fahrenheit. They've got competitors out there. Siemens has their own version of SLC that works similar. EST has their own version that works similar, but's different, and the same with Simplex, the same with Potter. All the different manufacturers do kind of basically the same thing, but they do work just a little bit different. So just always be aware of what you've got and what you're working with. And one other thing, and I know we've said it multiple times, everybody gets our submittals when we send these out. It would behoove you to take some time, and I know you do what everybody else does. You get the submittal, you look at the cover page, you might look at the bill of material, you thumb through all that other stuff in the middle and go to the drawings to see what you're doing. If you don't know the products, if you would take some time and actually read those data sheets, there's a lot of information in those data sheets that's just good to know. We can't sit here and read all the data sheets for you, just for your general knowledge, for your skill level as you grow and progress in your trade. That's just, there's just a lot of information out there that, we don't necessarily need to sit here and read you, but we actually provide. So anyway, I appreciate everybody showing up for this and participating. We're going to keep these classes up, and we'll just let you guys know what we're going to do next. And that's all I got. I appreciate all your help. I appreciate all your hard work. Thank you.
I thought of one more thing while Mike was talking. Using a meter to look at these SLC circuits, it's got a big difference in it if you're checking for voltage than if you're looking at a NAC circuit. Those NAC circuits are going to hold at a very steady voltage. It'll be 24, 27, something like that. But it'll be very, very steady. You won't see a lot of fluctuation in the voltage reading. When you're looking at the SLC circuits, because of that two-way communication that's constantly going on, you're going to see the voltage on that circuit bounce up and down. And I expect to see it anywhere from like the 18 to 20 volt range. I've seen some notifier systems that might have been closer to like 16 volts, but it's going for the Silent Night and for the Gamewell stuff. I've seen all of that is typically it's around the 18 to 20, and it just bounces around. We call that the polling. That's kind of how we refer to that communication between the devices and the panel, is it's polling. If you see your SLC circuit and you're going out there and like everything in the building is missing and you put your meter on it and it's just putting out like a solid 20 or a solid 24 volts and it's not bouncing up and down, you're not seeing that polling voltage fluctuate, that could be your problem. That could be an indication that your panel is bad. So yeah, I thought about that while he was talking about the voltages and what it does at the panel, and I was like, oh, I need to mention that. So I think that really is everything this time, unless y'all have some questions.